And this is what I can show you. I have a demonstration set up on this air track, and we do it on an air track, so there is a minimum of friction. And we're going to push two cars together, and we hold them together with a spring. The spring is like the explosion, like the dynamite that can push these apart. So here is one car on the air track, then there is a spring, and there's another car. Let this mass be m1 and this mass be m2, and this surface is nearly frictionless. And I hold them together with a string so that I can pull the spring in. So this spring is compressed, and the whole system is at rest. V equals 0. So there is potential energy in that spring. I take a burner, and I burn away this thread. This is the situation before. Momentum before is 0. Total momentum afterwards will also be 0. It's identical to what I did there. And so this object will fly in this direction, and this object will fly in that direction. And you already can tell what the ratio of the velocities will be, because you will see that v2 prime divided by v1 prime, you see it right there, equals m1 divided by m2. And so I will make some predictions about the speed of these two objects. The largest mass, by the way, would get the smallest velocity. And the smallest mass would get the largest velocity, the largest speed. What you see in here are really speeds. We don't have the information on the direction anymore. How do we measure the speed? Well, we actually measure the time for the cars to move 10 centimeters. Each car has a little metal plate which is 10 centimeters long, and it blanks out a light-emitting diode. And the moment that the light-emitting diode is occulted, the timer starts, and the moment that the light-emitting diode emerges again, the timer stops. So that's the way we will measure the time for each car to move by 10 centimeters. The first experiment that I will be doing, M1, is 244 plus or minus 1 gram, and M2 is also 244 plus or minus 1 gram. In other words, the uncertainty in the masses is something like 0.4%. That's just part of life. I can't do much better. The time that it takes for object number 1 to go 10 centimeters is obviously 10 divided by v1, which is the velocity that we want to compare them with. Now, the 10 centimeters is really only known to an accuracy of about 1 millimeters. So that is an uncertainty of 1% in my timing, in my velocity. So this is a 1% uncertainty. So if we measure the times that object number 1 and object number 2 will go through this timing device, a measurement of 10 centimeters, you would expect the times to be the same to within roughly 1 plus 0.5, say 1.5%. There is, however, an additional problem that is very difficult for me to evaluate, and that's the following. If here is that light-emitting diode, and here is that metal plate that I mentioned to you, which comes over this diode, occults the diode, and says, start the timer, and then the other end, of course, moves off, and then the timer stops, that criterion for on and off for one diode may not be exactly the same as for the other. Here is one system, one car will fly in this direction, and here's another system, and the car will fly in that direction. And that's not so easy to evaluate unless you do a lot of experiments. So I would roughly guess, I'm always on the conservative side, that this may add an uncertainty in the criterion of the diode of another millimeters. And so effectively, I really don't know any better than 2 millimeters what the 10 centimeters is. So I would say we really have to allow here for 2% plus 0.4%. So I would predict that the times of these two cars will be the same to within roughly 5%. That would be my prediction. So we're going to write down here the times, and then we're going to measure them. So time 1 and time 2. And we will see whether these two numbers are the same within the uncertainty of our measurements. Here is the air track. Have to turn on the airflow. Oh, let me tell, for those of you, for the parents in my audience who haven't seen this one, this is a marvelous device. It is a track which is well constructed so that these cars fit beautifully on this V-shaped track. And then we blow air out of this track, which lifts these cars up so that they float. And so we can move them in horizontal direction with extremely little friction. There is no metal touching metal. The only friction you have is the air drag. That you can never avoid. When you go through the air with a car, there is wind, the same wind that you feel when you drive your bicycle. But it's very little, and that's why these experiments are done on these air tracks. These are not cheap, by the way, these air tracks. They're very expensive. Well, you pay $25,000 tuition, so you might as well get something for it, right? So I hope that these timers are on. They are. And now we have here one car. And notice how frictionless it goes when I touch it. It's very nice, almost frictionless. And here we have another one. And they have equal mass to within 1 gram. And there is a spring between them. Some of you may be able to see it. And I'm going to attach now that string to hold them together. And so I put potential energy in the spring by pushing them together. And they're lined up now here. They have no momentum. The timer is not on. Has to be reset. Thank you. They're now both 0. Yeah, you sure? Okay. So now I'm going to burn off that wire. The momentum of each one of those cars will change. One will go in this direction, the other one in this direction. Kinetic energy will increase. That's the potential energy from the spring. But the momentum of the system as a whole, after I burn the wire, will remain 0. Ready for this? Make me happy. What do you see? You're going to make me unhappy? I better walk around. I can't wait. 220. Ah, fantastic! Absolutely fantastic. 223, 219 milliseconds. That is well within the uncertainties. What was the number? 219? 219 milliseconds and 223 milliseconds. If I repeat the experiment and I make the string shorter, I will get different times. I can never predict the times, because if I make the spring more squeezed, then obviously I will have more potential energy. And so the speeds of the cars will be higher. But the times will be the same within the uncertainty of the measurements. So I can never predict the time. Now we're going to do an experiment whereby I'm going to make M2 twice the mass. M2 is 488 plus or minus 1 gram. Now that's going to be interesting, because now you really begin to test the conservation of momentum. The momentum before is 0. I burn the wire, momentum afterwards is also 0. But the velocities, oh, I erased this, v2 prime divided by v1 prime equals m1 divided by m2. And so twice the mass will get half the speed. And so now you're going to see that one car will go twice as slow as the other. That's the only way that nature can conserve momentum. Nature has no choice. Nature can deal with kinetic energy one way or another, but it cannot finagle momentum. So it must give the more massive car half the speed than it gives the other car. And so we're going to redo this experiment now with a car here which is twice the mass, and this one is 1's mass. So this is the 244, and the one on your right is the 488. So I have to bring them together again with a string. So I do the work now. I always do the work here in 26100. I do the work. I squeeze these springs. I get paid for that, by the way. And that's potential energy if it goes into the spring. There it is. Momentum is 0. Kinetic energy is 0. I have to zero the timers. Oh, and I would like to make a prediction. I would like to see, we'll measure T1, and then we'll measure T2, and then we get a number, and we get a number, and if we multiply this number by 2.00, then I would like to get this number. Within the uncertainties of the measurements. There is always an uncertainty in any measurement that you do. All right? Make sure that, are the timer 0? Okay, there we go. What do you see? Ah, 406, 193. Whew! On the button! 406 and 193. 0.406, is that what you see? Yeah? And 0.193. Now I don't even need my calculator to multiply this by 2. I can even do that by heart. 9, 3. .396, 0.406. Close enough. The two are in excellent agreement within the 2.5% uncertainty in each measurement. So you see, that's exactly how you can demonstrate the conservation of momentum. They picked up kinetic energy, but after the wire was burned, the momentum remained 0.